This tube is an electron diffraction tube. Inside this tube, you've got some graphite right here at the end, and an electron gun here, and you're going to have the electrons accelerated through a potential difference, and then they're going to strike this graphite, be diffracted, the electron waves will be diffracted, and then this fluorescent coating will glow, showing where the electrons arrive and showing the diffraction pattern. So I'm going to show you how to wire this up. You're going to need one of these, a high tension and extra high tension power supply. This one I wouldn't necessarily recommend. The screen can be a bit flaky on it, but it works. So the first thing you're going to do is to connect the heater. In the back of the tube, you can see there's two connectors, and you're going to just connect these up to the 6.3 volts AC of the EHT supply. And that's going to be your heater. That's going to heat up the cathode, the filament, the tungsten filament, which is going to start glowing. And you can just about make out the glow inside here. I'll give it a little bit of time to heat up, and then when it's heated up enough, you'll be able to see there's a bit of a, you might just start being able to see it inside there. Let me turn all the big lights off. There we are, room's a bit darker now, and you can see there's an orange glow coming from inside that, from inside here, from inside that cathode. Right, let's turn the lights back on so you can see what we're doing. Okay, so this tube has another connector. Now the connector broke and I had to solder this dodgy wire onto it. I had another connector. I've tried wiring this up several different ways. And the way I'm going to show you is the way that seems to work best. It's not the only way of wiring this up, but it seems to work okay. So what I'm going to do is I'm going to connect to this extra wire, this dangling wire that's connected here. I'll connect that to the earth. Now that means that the cathode is now at 0 volts potential. It should be at 0 volts potential. It's got an AC across it, so it's going to be heating up still, but 0 volts potential. We've got thermionic emission of electrons from that cathode. So now we have to encourage those electrons to move away from the cathode. We have to accelerate them forward. So to do that, what we're going to do is use the EHT part of the supply. Now, I want to set up the electric field pointing this way. So the electric field pointing this way. So I want this side to be positive and this side to be 0 volts. The other way of setting this up is so that the anode over here is at 0 volts and the cathode is at a negative potential. And that will do the same thing. But I haven't been able to get this one to work set up like that. So let's carry on. At the side here, connected to the anode, there's a connector. What I'm going to do is I'm going to connect to that connector a wire, and that wire is going to be connected into here. Now I'm at the moment going to stick it into the protected supply here. It's got a 50 million ohm resistor protecting it. Can you see the screen is flickering and glitching all over the place? It's not great. And the other thing I'm going to do is connect the negative part to the earth. They always tell you should have it turned off when you plug things in. I'm sure that's very important. So you can see the wires there. And it's the same principle with all these tubes. 6.3 volts AC across the heater. If you then earth the cathode and connect the anode to a positive potential, then you get electrons accelerating. Now with this tube, I've found that you don't get very good dot over here if you have the protected side. I stick it in the unprotected side without the 50 million ohm resistor. You get this lovely pattern here, and I can adjust the pattern like this, and it works very well. Let's just turn the lights off so you can see it more clearly. So, I mean, it might be coming across a bit too bright, so let me try and adjust where the brightness is on the camera there. Reduce the voltage, the potential difference, and I mean, you might just be able to make out that the circles are becoming wider when I reduce the potential. If I turn this around, it might be a little bit clearer. Might not be. Might be a little bit clearer. Again, I'm going to try and adjust the brightness to this point right at the end. So you can see there's a dark circle. You can see the potential difference on the screen. That's in thousands of volts. I reduce it, the dark circle widens. And then another way the camera automatically adjusts brightness. The background brightness seems to be changing. Right, let's try focusing. Oops, there again. Come on, you can do it. There we are. Dark circle getting wider as the potential difference reduces. And you can measure the diameter of this dark circle. You can measure the geometry of this particular tube. And then you can use that geometry of the tube and the diameter of the circle to determine the diffraction angle, pop it into your Fraunhofer far field diffraction equation, and use that to determine what D is. You need to know what the wavelength of the electrons are, but you're accelerating the electrons across nearly 2,000. Let's make it exactly 3,000. Let's make it exactly 3,000. Across 3,000 volts. So you can calculate what the de Broglie wavelength of the electrons is pretty easily. So that's electron diffraction. We've got plenty of other tubes, so if I take this one out, place it over here, and get another one. This is our Teltron D tube. This is used for electron deflection by electric and magnetic fields. And it's very easy to connect. It's the same as the other one, except it's only got two connections at the back now. So you take, just as we did before, 6.3 volts AC. Connect it there. Another 6.3 volts AC connector into there. This time, what we're going to do is we would do the same thing in terms of the earth, because I do find it works better that way. We'll earth, doesn't matter which of these you connect it to. You earth the cathode. So that's now connected like that. Then we want to earth the negative part of the high tension supply. So that's just a wire going back like that. And then we're going to connect the positive part there, that's the anode. Here, we're going to connect that to, again, I'm going to use the unprotected part because it works far better. And when I whack that up, yes, it's always frustrated me that the card is angled that way around. When the scale is on this side, I think the card should be angled the other way, because you get this really beautifully bright blue line on this side where the scale is not, and a much dimmer line that side where the scale is. That's always bugged me a little bit, but okay, it doesn't really matter. It works fine. So how do I get the electron to deflect? Well, I'm going to need another high tension power supply, another EHT power supply. So here's my second EHT power supply. This one, I'll put tape on it because the screen doesn't work properly on this one. Like I said, these aren't the best power supplies out there, I don't think. The big old metal ones work far better. I've got a couple of them next door, but I'm not moving them for this. So, we're not going to adjust anything. Let's move the camera back. We're not going to adjust anything here. That's all fine. We do want to connect a potential difference across here. So that's where this comes in. Dead simple. Negative, and we can connect that to either of these terminals. I often find that the wires aren't long enough, so I have to use these adapters. Far better than shoving the wires one in the back of the other. To do that, and that needs to go onto the bottom there, so another adapter, have a good supply of them. And so that's your wire there. You can see that clearly enough. Connected to the bottom, connected to this, with those wires out the way, connected to this high tension supply. Then Again, unprotected, I think works far better. People are going to shout at me and say, oh, it's not safe. Oh, it's fine. Don't fuss. It's fine. Again, the wire's not quite long enough, so I connect with an adapter onto there. And now I can deflect my electrons. This one doesn't work very well. I can't change the deflection. Let's get the lights turned off so you can see it more clearly. Let's get that over there so you can see both screens. Right, back in a second. So you can see that's being deflected up by this electric field. This isn't working very well because I haven't got a huge range of potential differences from this one. You notice it's a little bit spread out. If you just earth the negative one, you get a much more defined beam. It's much better. But still, I don't have much play in this. It's not changing very much. I should perhaps get the other power supply out to show a decent variable potential difference, or one that you can actually read, because that would be useful. I'm not doing it now. Right, so magnetic deflection on this one. You're going to need another power supply, a third power supply. However, this one's going to be just a regular old power supply going up to about 15 volts. Where am I going to put this? I don't have enough room on my table. Let's move some of these out the way. Let's move that one back there, that one back there, and pop this one here. Because we're not going to touch any of the other stuff. Right, we're going to use that to deliver a potential difference across, and therefore a current through, a set of Helmholtz coils. I'll plug my power supply in. Check it works. Good. We're going to use some Helmholtz coils. And here they are. They are sets of coils like this. They have 320 turns on each coil. A maximum current through them of 2 amperes. There's the other one, here it is. My other ones had to be repaired, but I believe it's still got 320 turns. So those are your 2 coils, and you arrange them. You need to be able to get to the plug holes, so you arrange them like that. Okay, like that. And the Teltron tube base has something they can slot into. A student 3D printed one of the connectors at the bottom because one of ours went missing. Right, now we just have to connect up the Helmholtz coils. To do that, you're going to need 3 wires, 2 of them far longer. So I've done my usual. Here's one of the wires. I've added a connector to make it longer. And we're going to connect that to the positive side. We've got it back to front, we can switch it later. And let's pop that into Z. Then, the negative side with another very long cable, again connected with an adapter in the middle, to the negative side of the normal power supply. And that also goes into Z. And then with the shorter cable, we just connect A to A on the other side. Now when I switch on the power supply, okay, I've got magnetic deflection, but it's going the wrong way round. So let's just switch the polarity. Now we've got magnetic deflection. Let's switch off the electric deflection for a second. You'll notice that it's spreading out the beam. Right, let's turn the lights off again. So you'll see the electron beam is being spread out. What we want to do, we want to stop that so it's not being spread out. We want it to stay together. The reason for that is that this isn't a wonderfully smooth supply, so we need to smooth it down. And that's where I'm going to get another 2 wires. There's a lot of wires in this experiment. Another 2 wires, 2 crocodile clips, and an electrolytic capacitor. You've got to be careful when you connect your electrolytic capacitor to make sure you're connecting it the right way around. There is a sign on it that says negative, you probably can't see that very clearly. There's a sign on it that says negative is this side. So with one of the wires, I connect it to the negative part of the electrolytic capacitor and connect that to the negative side of the power supply for the Helmholtz coils. The other one, I'm going to connect to the positive, and I'm going to connect the other end of that wire to the positive. Just watch what happens to the electron beam. There we go. much better. So, not the best coils, but they're not bad. We get circular deflection. When it strikes the metal plate, something funny is going on there. I could disconnect that, that'd be better. So we've got circular deflection, as expected. But if I connect up the electric field like that, I can adjust the magnetic field and the electric field to get a fairly straight beam, as straight as I can manage at least. And then I know the magnetic force and the electric force are pretty much balanced. And I can use maybe a Hall probe to measure the magnetic flux density from these Helmholtz coils, or I could calculate it. There's an equation you can use to calculate the magnetic field, the magnetic flux density in the middle of some Helmholtz coils. For that, you're going to need an ammeter connected in series with the coils, which is not a problem. You just whack another wire in with another ammeter, fine. But there we go. No magnetic deflection, no electric deflection. Let's turn that, oh, we have to earth that. No electric deflection. There we go. No electric deflection. Plug these back in. Electric deflection and magnetic deflection. Right. There's another tube. That's the Teltron D tube for electron deflection by electric fields and magnetic fields. There's another tube. Although I would say that this experiment uses the most wires by far. Good job you know what you're doing when you connect it up. Right, so another one. Let's get this tube out. Right, in fact, we've got a couple more tubes to show you. But let's just take this Teltron D tube out. Don't need that. What box did it go in? Oh, no, I have to find out what box it went in. Yeah, they're quite expensive, so I don't want to break them. Right, this one is called the Maltese Cross. Looks like that. Same thing, you insert it into the tube holder. The back end, exactly the same, 2 holes. Exactly the same, we're going to be using an EHT supply. So let's get some wires out. Now, just like last time, we're going to connect 6.3 volts AC to heat up the cathode, tungsten filament. Just like last time, we're going to earth that. Now, I know there's another way of doing it, but this power supply, for whatever reason, really doesn't like it. I think that's how I broke the other one. I'm also going to earth the negative terminal and connect the positive terminal. Again, I prefer to use the unprotected part because it works better. With a nice long wire. Actually, I don't need the nice long wire. I could just use this adapter. Shove it right in the bottom there. And also this one here. Right, I did that without telling you what I was doing. So let's take it back a step and let's talk it through. Back a step. We should be okay with this part. We've earthed the cathode. It's at 0 volts. So we need a positive potential at the anode and a positive potential at the Maltese Cross. Now the other way of doing this is to earth the Maltese Cross, earth the anode, and have the cathode at a very high negative potential. And that does work, but it breaks my screen. So I really don't like doing it. So positive for the anode goes into the side here of the tube. That then goes to there. The negative connection is going to be earthed. And we also want to have the cross itself at the same potential as the anode. So connect that wire down there. Connect it. I'll just shove it in there this time. Actually, it doesn't matter. I'll shove it here so it's a bit tidier. Now, if I turn that on, you get this gorgeous cross. In fact, if I disconnect the anode, you can see, although it's probably not very clear, just about the shadow of the cross here. If I turn the lights off, it'll be clearer. You can see the shadow of the cross over here, caused by just the fact that tungsten filament is heating up, and you can actually see it. You can see the glow coming from it from inside there. But as soon as we connect the potential there, we then get that beautiful Maltese cross shape. And you can do things, you can connect your Helmholtz coils again. That's quite a nice thing to do with that. So you can cause deflection with the Helmholtz coils. The other thing I like doing is taking a magnet like this, a sort of cylindrical magnet, not a square one. And you can get deflection, so it kind of gets deflected down and kind of gets deflected up, but it's not uniform. So we could talk about the shape of the field. And the reason why I do that is because the really fun thing is when you move the magnet towards the front and the Maltese cross shape seems to twist. And that really helps students get their head around visualizing the three-dimensional magnetic field shape around this sort of magnet. So I think that's quite a good thing to do, especially before you move on to magnetic lenses in electron microscopy, in transmission electron microscopes. So that's your Maltese cross, pretty straightforward to set up. The other one we've got is a fine beam tube. Let's take the Maltese cross out. Yeah, the fine beam tube is quite nice for showing magnetic deflection. Can't really show electric deflection, but you can show magnetic deflection. Here it is. This is quite an old one. It's got a switch here for switching between the two different cathodes. If you look really closely inside here, you can see there's one cathode here pointing that way and another cathode there pointing upwards, so you can get circular beams. This one really needs a dark room, a really good dark room, and this room probably isn't dark enough for us to demonstrate this to its full. Anyway, usual method, let's go with 6.3 volts AC there. And actually this one's an interesting one. I've just connected it and remembered. This doesn't use the EHT supply. You're not going to damage it if you do use the EHT supply. It's just not going to work properly. You might see momentarily the fine beam and then it's going to vanish. So we're going to get rid of that, move that to one side. Instead, we're going to use the high tension supply, the HT supply. This can supply up to 350 volts. The EHT can supply up to maybe 5,000 volts. This is up to 350 volts, but it's got the same 6.3 volt AC heater right there. So although it's a different supply, it's exactly the same connections. You just connect 6.3 volts to one side of the heater and the other side of the heater. AC, that's going to heat up the cathode, which is going to cause thermionic emission. We earth that, so we just connect that through to this little green hole there that's labelled earth on this particular one. Then we're also going to earth the negative connection of the high tension supply, same as we did with all the other tubes, and the positive connection of the high tension supply we're going to connect to, and I'm going to connect it to both of these anodes because we're going to switch between them. There's no point having it only connected to one. So there's one of the anodes there. The other one is connected on the other side, and I'm just going to connect this wire straight round and pop it into the back of that anode there. So probably not going to be dark enough to see what's going on here, but let's switch it on. If you hear it crackling or fizzing, it means you're using too high a potential. Right now we're on 250-ish. 250. You can see that the filament is glowing. It's got that orange glow inside there. It takes a while to warm up. When it's warmed up, you see there's a blue line going across, or a greeny coloured line going across. And that greeny coloured line is deflected by magnetic fields. Look. Just as we would expect. Might just be able to see that line. See if I can get the contrast a bit better. So you can see that that line is being deflected. That's because there is a gas that fluoresces actually in this tube. So we can see that beam nice and clear. If I switch the switch, it'll take a little while because the other filament has to heat up, but we'll start to see a beam emerging upwards. It's not going to go anywhere, can't really go anywhere, because the tube is in the way. In fact, you can see a mark on the glass here where the electron beam struck it lots and lots of times. So you can see that actually there. But what I can do is grab my Helmholtz coils. Plug my Helmholtz coils in, just as we did last time. Like that. Can't see what's going on yet. There's just the electron beam going up there, can't go anywhere. Let's get those Helmholtz coils powered up, some current going through them. I'm not going to go through how to wire it up again, because I've shown you that before, but remember it's A to A and Z to Z. And then if I increase the magnetic field, smooth the camera so you can see it a little bit more clearly perhaps. Hopefully that's going to be clear enough. Might be a little bit too bright. Is there a way of me adjusting the brightness? There's a brightness slider somewhere. There we go. So higher magnetic field, lower magnetic field. You can see the electron beam is being twisted into a circle. If you get it just right, you get this line appearing on the screen. No line, it's too tight a circle. Bit of a line, no line. If you want a tighter line, obviously we need our capacitor again. So just about to connect the electrolytic capacitor and bang, look how well defined that is. Really clear. So that's your magnetic deflection of electron beam causing circular path. And if there we are, it's just touching the fluorescent screen and now it's not. So that is not a high enough magnetic field. Then it's higher, then it's too high. So you can use that if you know the diameter of the tube, you know the magnetic flux density and so on and so on and so on. You can see the filament here is getting hot enough to glow. That's really hot, so I'm not going to leave that turned on for very long. That's making me feel nervous. Let's turn that off. And there we go, that's the fine beam tube. The one I haven't shown you yet is the Perrin tube, but I think I've shown you enough. It's the same principle with them all, just AC 6.3 volts, then potential difference.